Hey everybody, Lars here. Welcome to the Halloween edition of Unit 4's Recursion video. There's no chance I'm keeping this thing on for the whole thing. And even though I got this for $5, I'm just going to put it in the cave and just leave it around there. That's not the mask that I use when I'm breaking into airlines and taking down currencies and other governments. This is the one that I use for that. But I digress. Time for the second and last review video for Unit 4. And forgive me in the middle of this video, and I'll keep it running too. I may get trick-or-treaters. All right? I live on a dead end. Sometimes I get kids, sometimes I don't. Sometimes there'll be an organized bunch come down the road, so there'll be 20 of them. If they come down here, they're in good shape because I got the big blow pops, not the little crappy ones, the little crappy Tootsie Roll little ones. I got the big boys, the nice ones, because that way if the kids don't take them, then I can have them, and I like the nice ones. So, it's always a good reason. But, it's 5 o'clock on Tuesday, proving once again that there's no such thing as a vacation day at Rutgers University because my research group didn't meet today, so I took a day off because I had no meetings and I had no planned things to do, no tutoring, no advising hours. So, I took a day off and I've just been sitting here the whole day answering my emails. So, until the semester ends, there's no such thing as a vacation day at Rutgers University. There's no rest for the wicked. In keeping with that, we are going to bang out a video on recursion. Recursion usually is considered this scary topic that's hard to understand. And it's really not. Most people here, let's start here. I am doing some database stuff, but what I wanted to show you was the Wikipedia page on recursion. If you look at it, it's not just computer science, kind of like FizzBuzz. It had a life of its own, and then computer science found it later. Recursion, basically, in its simplest form, is something that refers to itself. Its applications are usually in math and computer science, and you'll see that in a section. As you can hear, you can see the Drost can that has itself in its own drawing, and snakes that eat themselves, and Escher. I'm not going to find it, but I used to have an Escher picture done in Legos, which is pretty neat. I'm sure you've seen the hand that's drawing itself on either side. When you get to computer science, you're talking about things like Sierpinski's triangle and things that refer to themselves. And when it's first introduced, it's usually always introduced with a function that refers to itself inside that function. And that sounds crazy. As you can see, Factorial, that's actually what we're going to do, but we're going to do it in a little different way. And you can get all the crazy formulas down here. Basically, and I'm going to code something up real quick. Hopefully this is going to be a quick video, because I'm going to go through a couple of different recursive functions, but nothing crazy. But this is the story. You take your first course in computer science at university, Intro to Computer Science, and you'll learn a little bit about the language, be it Java, C++, back in my day it was Pascal, and you learn a little bit about the languages. Then you get sorting and searching, which you're doing in the first part of this unit. You learn about how important it is, how to do a sort, how to do a search, and you start practicing using the language by playing around with those two topics. Well, then eventually you get to recursion, and classically in computer science, we are shown recursion in either one of two ways. Either we use recursion to produce the Fibonacci sequence. Now, if you don't know what the Fibonacci sequence is, it's 1, 1, 2, 3, 5, 8, 13. The next number in the sequence is the sum of the two numbers that came before it. Okay? And you can create a function that recursively generates that particular sequence of numbers. Also, we do factorial. You're going to see why in a minute. Factorial is a list of numbers all multiplied together. If I say 5, it's 5 times 4 times 3 times 2 times 1, which is 120. Okay? That's factorial. This has always been my issue. You're getting this, usually, 80s, 90s, 2000s, when you're 19, 20 years old, because that's when you're going to your first year at university. And a lot of students, some have seen it, some with math backgrounds, but a lot of students have never seen Fibonacci or factorial before. And the point then becomes, in my mind, is that you're not seeing something done differently. You're seeing something for the first time. So it's not like there's a regular way to do this and then there's a recursive way. It's like, well, this is the way we do Fibonacci, this is the way we do factorial. It doesn't really register in people's heads that this is a different way of doing things. So what I do when I teach this particular topic, because I'm a schmotty, is I do things that you've seen already in the past, like sums, like multiplication, like exponentiation. So that you know how it's done the regular way, I'm going to show you how to do it recursively. And in that vein, I'm just going to whip up something right now, a quick function called mySum. And what I'm going to do is if mySum, and I take an argument called n, and I'm going to say if that n comes in and it's equal to 1, then I want to return 1. All right? Else, and this is the trick, return n plus mySum of n minus 1. Okay? Wrap your heads around that. All right? You're going to see in a second it's fine. I'm referring to this function itself. All right? Even before I was done writing it, I referred to it because I'm going to use it again. All right? Let's run it first. See what we get. I'll say A is mySum of 6, and then I'm going to print A. Save that, run it, and I get 21. That is correct. If I take it down to 5, you'll see that it's 15, and so on. So it works. So what's actually happening here? What's happening is I'm going to assign to the variable A the result of mySum of 5. MySum is the function name, channeling unit 3. 5 is the argument. I come up here, mySum of 5. Is 5 equal to 1? No, 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 no. So I go to the else, return 5 plus, and then I call it again. But I don't call it with a 5, I call it with a 4. Okay? Let's think about it. What do I want to do now? I want to do the same thing, except I want to do it with the smaller list. So I call it with 4. So what happens here? MySum of 4. Is it equal to 1? No. Else return 4 plus, do it 1 less. Come up here. Is it 1? No. Else return 3 plus, and minus 1, 2. Boom, boom, boom. You'll see that when you finally ratchet it down to 1, it'll say, is this 1? Yes, then return 1. Where will that get returned? To this. It'll be added to 2 and returned to what? To 3 plus 2. And that'll be returned to what? To 4 plus, and then whatever the number is, and boom, 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 all the way down the line until you get to the very last call, which will give you 15. Okay? We're going to kind of see that in a moment. So this is how a sum would be done in recursion. You can see the key right here is that plus sign. Because as we come back up the stack, it's that plus sign that's going to be executed every time. All right? This is going to be easier to understand in about 2 minutes because I'm going to trace one in a different way. All right? Now, this is the important part because look, if I change that operation and I rerun it, 120. Now I'm doing factorial because I'm doing 5 times 4 times 3 times 1 times, I don't do the 0. I'm going to tell you right now, and this is going to be a good way for me to know who watches the videos and who doesn't watch the videos. See that n equals 1? That n equals 1 should be a 1, okay? Because a lot of people, and I don't know where they're going to get this bad information, will put 0 there and test for a 0. Now, here's the funny part. Watch. It works, okay? And the reason it works is because you're doing an extra multiplication, but that extra multiplication is by 1. So it's an identity, and you're getting that answer still. The thing is, it's inefficient. You're going one more time than you have to. There's no reason to multiply by 1. So you shouldn't be looking for n equal to 0. You should be looking for n equal to 1. All right? I'm going to ask you, I'm going to see if you guys watch the videos. When it comes to quiz time for Unit 4, I'm going to ask you to write me a recursive function. All right? N equals 1 is what I need to see. I wish I had $1 for every time somebody put n equals 0. All right? I want to reduce it down to it's at its smallest point. that it makes sense for our particular thing. This I wouldn't call my sum. I'd call my factorial. But you know what? I'm going to change it back to sum. Okay? So now when I run it, it should give me 15 again. All right? So that's what's going on with recursion. One last thing, and after I run through my second example, hopefully it'll straighten things out for you. Don't think of, when you trace through code like this, don't think of this going up here and getting all down a rabbit hole and only using this area when you think about it. When you call my sum here, think about getting a fresh blank copy of this function over somewhere else. Because that's exactly what's happening in the real world. My sum is saved in memory. And when you go to use it here, we just get a copy of it and put it in memory. And then we run it, and then it calls my sum of 4. So what happens? We get a fresh copy, and we run my sum of 4. And what happens there? Well, that asks for my sum of 3. So we get a fresh copy, and we come down, we do my, then 3 gets done. It goes back to 4 because that's where the call came from. 4 gets done. It goes back to 5 because that's where the call came from. And then when you finally get the answer, you report back, you assign it to that variable, and then you print the variable. All right? We're going to see this in a different way. My sum is going to go up on your Sakai resources, so you got no worries about that. The second thing I usually show people is multiplication. Okay? The way to do multiplication recursively, you're looking at it right in front of you. What do? You say the number and how many times. All right? That's what multiplication is. All right? I mean, at the end of the day, what's multiplication? It's addition on steroids. So we just want to add something that many times. In this case, I do 3 times 3. All right? You're going to see why in a minute. So I come in and I say, is times equal to 1? No. So I go else, return num plus my mult num times minus 1. So whatever the number is, in this case 3, now I call my mult, same number, 3, but I say 2. Because now I want it 2 times. I come up here, num is 3, times is 2. Is it equal to 1? No, it's equal to 2. So I come down here. I got 3 plus my mult, num times is now 1. I come up here. Is times equal to 1? Yes. So I go back up the stack. And I perform that plus operation as I go back up. And you're going to see it a little bit better now because I'm not going to trace it like this. We're going to trace it like this. Okay? I am notorious for being a bad number drawer. All right. My mult, num times, num is 3. That's not so bad. And that's 3 as well. Woohoo! So, is times equal to 1? No, it's 3. So, else, return num. What's num? 3. Plus, my mult, num, which is still 3, times minus 1, which is what? 2. So, I'm calling it my mult, num times minus 1, which is 3. So now, where do I go from here? Well, I want to call my function. So where do I go? Right here to a fresh copy. Num is 3 times is 2. Is times equal to 1? It is not. So return num, which is 3. And we're calling the function again. My mult, num, which is 3. Times minus 1. Times was 2 here, so minus 1 makes it 1. Okay? Now, where do I go? Here to a new, fresh copy of the function. Num is 3. Times is 1. Is times equal to 1? Yes, it is. So, I return num. What is num? Num is 3. So, this function returns a 3. Where does it return it? Right here where the call was. So, this entire thing here came back as a 3. So now we're ready to return this. What is this? Num 3 plus 3. So the answer here is 6. Where does that 6 go? Where does that 6 get returned to? Right here. Okay? The result of this entire thing is 6. So, Now, from this function, I'm going to return 3 plus 6. So what am I going to return? 9. And where am I going to return the 9 to? I'm going to return the 9 to right here where it was called. A assigned my mult 3 of 3. So when I run this, I get 9. Okay? That's what's going on behind the scenes. If I added 1 to this, then my times would be 4. I would rerun it, and now I get 12 because I'd go through the process one more time. That's all that's going on. That looks crazy. You saw it from the beginning, so you understand it. But that's all that's going on with recursion. I'm grabbing a fresh copy, and I'm running the same. I want to use the same idea inside of the idea. All right? It's not that crazy. At the end of the day, it's you wanting to repeat a process over and over again before you finish it, in a sense. Okay? This is where it gets not difficult, but where it gets nuanced is recognizing when you can use recursion to solve a problem. That's the nuanced thing in computer science. And the way we do it, which is the way we do a lot of things as humans, the way we learn is we're mimics, is we practice a lot. We see a lot of examples. And eventually we abstract out those features of those particular problems which lend itself to recursion. All right? At the end of the day, what you're probably saying to yourself now is, you know what? That's great what we just did. Congratulations. But I think the way I multiply works and I don't need this crap. And my answer to you would be, you're right. But in computer science, there are a lot of problems that lend themselves to recursive solutions. You're going to learn about binary trees, and a lot of times you can store things in binary trees. And when you have a binary tree and you're searching through it, you go to the left. What do you have? Another binary tree. You want to go to the right or the left? What do you have? Another binary tree. So recursive solutions like this often work well in those contexts. Because you're like, oh, I'm going right. Do I see what I see? No, do it again. I'm going right. Do I see what I need? No, do it again. Do I see what I need? Well, yes. Okay, then go left. Okay, now go back up. Now blah, blah, blah. And it lends itself to recursive solutions. So recursion comes into play later on. At first, we give you Fibonacci and Factorial and ask you to wrap your head around referencing something before you've finished writing it. But it's not all that bad, as you can see. You've already gotten 2 or 3 examples, because I know in the Zell book they did I'm sure they did Fibonacci, I'm sure they did Factorial. You saw me do a sum, now I've done multiplication for you. So you have a whole boatload of examples. I don't know if I want to save this, so I may just cut it out. Discard changes, because I always want my blank, because I'm going to end up doing this again in spring. All right, but I am going to put multicur and my sum up on Sakai, so you have it to play around with and do things with. And if you want, take my sum and make it my fact and make it a factorial and do a bunch of stuff like that. All right? All right. Then, announcements. You know what the big announcement I'm going to give you is. Today is Halloween. Ooh, spooky. You've got 1 week. November 6th is the due date for the midterm. All right? I see people talk to each other in the group forums. I think that's good. Probably this coming weekend, even though now that it's been moved from evil Yankee Stadium, the Maryland game is on Saturday, so I'm going to be there this Saturday. But I'm still thinking I may trickle out some final project information, just so you can wrap your head around what's expected and maybe make some plans. I want you to concentrate on the midterm. I want you to do a good job on it. But A, if you're done, and B, if you want to, make some plans for what's coming, boom, boom, boom. I want to let you start to get a little bit of information about the final project, which won't be released in all its glory until the day we have class, the 7th, which I think is a Tuesday. Okay? So actually, you have 6 days. You don't have a week. The 6th is going to be Monday. All right? And you have to do your midterm. So do that. All right? Other than that, the boys are cranking away on your assignments and quizzes. You should have gotten assignment 1 back as far as feedback is concerned. I told the boys, I read them the Riot Act. I said people need to get feedback. If they get, if there's anything wrong and they don't get full points, they need to get feedback. Because a couple people had problems with that. Problem seeing it, problems getting it, asking what went wrong, blah, blah, blah. So I screamed and yelled at the boys, and everything should be fine. Same with the quizzes. If you do not get full marks on the end, you know the end of the quizzes when I ask you to code up a little something, something. If you don't get full marks on that, I told the boys, make sure you write down what the problem is. And you let people know, and you release that back to them so they can see. All that said, if you have a question, you're more than welcome to send me email, and I'll answer it for you. I'll let you know what's going on. So that's how we learn. We learn with feedback. I think it's very important. And if you don't understand why something went the way it went, ask. Because I want you to know. And I want you to understand things. All right? Other than that, we're in great shape. We're going to be in Fat City because we're going to have a whole bunch of extra time for your final project, and I might give you extra time for Unit 5 because that's what I try to, if things go haywire is a relative term, but if things get to the point where I think people need extra time for things, then I grant it during big semesters, fall, spring. And that really hasn't happened to us, so we've been on schedule. We've been right on schedule so far, but this class has been pretty good. So there's going to be a couple extra days built in there. I may just use them and give you extra time for Unit 5. We'll see when we get there. But, and this is going to be a little bit early, but I think I'm going to release the assignments tomorrow. So you'll have the assignments and you'll have a ton of time to get them done because I believe this unit ends a week from this coming Friday. So you'll have 9 days with all the resources and all of the stuff, the review videos, the Zell, the slides. And this unit isn't crazy. Like I've said before, this unit is a rest period between Units 3 and Unit 5. And Unit 5 encompasses the Thanksgiving break, I think. So you'll have a little bit of vacation time to just sit down one day and dedicate a couple hours to catching up on Python and doing stuff. All right? All right. Then I'm getting out of here. You know me. There'll be announcements, and we'll be in touch all along the way. But this is it as far as your resources are concerned. You've got the 2 review videos for Unit 4. Got a little bit of code up there on Sakai. Got your slides. Got your book. Should be in pretty good shape. Work on that midterm. Okay? This unit is the way it is because this is around where the midterm is getting done. Spend time doing that stuff, all right? Enjoy it. Figure out what you like, what you don't like. Let me know what you think the best way to learn things is. Is online okay? Would you rather do something interactive with a computer? Would you rather sit in a class? Let me know how you like things. All right? All right, I'm getting out of here then. You guys be good, and I will see you later. Bye. Hey, we did this whole video without any trick-or-treaters coming. Yeah? You know what? By the end of the night, I'm going to have a bowl of candy, and I shouldn't be eating it, and I'm not going to know what to do with it. I may reverse Halloween and go around my street with my candy and just pound on doors where I know there are kids. Go, 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 go. Trick or treat. When they open up, I'll just take the candy and throw it at the kids. I'll go, here, you lazy bastards. You should have come to my house and gotten this candy. Because I got nothing to do with it. What am I going to do with it? I ended up throwing it in the street. All right. I didn't mean to go into this Halloween rant. But it's true. There's a whole bowl of candy for anybody to take, and no one's coming to take it. Makes me crazy. All right. I'm getting out of here. I will talk to you. Well, I'll talk to you via announcements, but then the next time you're going to see me live and in person in a YouTube video is going to be the first review video for Unit 5. You'll like Unit 5. Unit 5 fun. All right, enough of this. I'm getting out of here. You be good.